let's do this. Let's investigate how to find the length of an arc, hence arc length, for a given curve. So let's start with something simple. Let's start with, oops, there we go. Something we should be able to do geometrically. Given a function y equals 2x plus 3, let's find the length of the graph from 0 to 5. So what does that look like from 2x plus 3? So it's basically a line, and I said from 0 to 5. So I don't know, something like this. And there you go. So I want the length of this curve from 0 to 5. Well, I know at 0 I'm at 3, and at 5 I'm at 13. Well, geometrically, I could just use, the distance formula. If you want to break it down to a right triangle and then use Pythagorean theorem, that's fine. But depending on who you had for geometry, you'd realize the Pythagorean theorem really is the distance formula, or the distance formula really is the Pythagorean theorem. That's probably a better way to say it. So the distance then would be the square root 13 minus 3 squared plus 5 minus 0 squared. Okay, so that's going to be, well, 125, which is 5 radical 3. There's the length of the curve from 0 to 5. Now obviously that worked nicely because this was just linear. What if it was all curvy and stuff? Curvy and stuff, let's see. Curvy and stuff would be something like this. Okay, and excuse me, what we're going to want to do is figure out the length of this curve from a given, A to B. So the cool thing is it's really the same idea as what we did here, but we're just going to do it in really tiny pieces. All right, so I'm going to just sort of say this is, my first point. I'll call that x1, and here's my second point. I'll call that x2, and I'm going to find this length right here. I know it's a straight segment as opposed to an actual curve, but you can imagine if we made this really small in between. One sec. If we made this really small in between, then the segments will almost look exactly like the curve. All right, so we're just going to try to make one segment to start. So if this is x1, this is x1 f of x1, and if this is x2, this is x2 f of x2. Okay? And I want to go ahead and find the distance between those 2 points. So the distance is going to be the square root f of x2 minus f of x1 squared plus x2 minus x1 squared. So it's basically just distance formula at this point. All right, so the distance between those 2 points is the distance formula. But this is kind of cumbersome, so we're going to write it a little bit of a different way. F of x2 minus f of x1 is really just the change in y values, right? So instead of writing it that long way, I'm just going to call that delta y, the change in y. And x2 minus x1 is just the change in x, that's delta x. Okay, and there's our distance formula in a bit simpler form. Well, we need to do a little bit of shenanigans to make this work, and the shenanigans are simply going to be to multiply this by delta x over delta x. Why do I want to do that? Because I want to actually get this denominator inside my square root. So if I do that, I'm going to get delta y squared over delta x squared over, I'm going to leave the numerator delta x intact. But if I want to get this delta x inside, it's going to be in the denominator, and it's really going to have to be the square root of delta x squared, right, to bring that in? So this is really going to be delta x squared, because again, square root of delta x squared gets me back to the delta x squared. All right, could I put it as one fraction first and then split it up? Sure, but hopefully you realize that it's the same thing. So this delta x in the denominator I brought inside by making it squared, because the square root of delta x squared would get me right back to this delta x. The numerator delta x is just coming along for the ride. I had to include it because I can't change the whole value. I'm just multiplying by 1. And this is where we want to start simplifying. So we simplify. This becomes delta y over delta x quantity squared plus 1. And then I still have this delta x outside. Now this should look pretty good. We have delta y over delta x. What's delta y over delta x? It's just slope, right? Isn't that the slope? But I want delta x to be really, really small, right? In my picture, I really want these two values to be as close as possible. So I'm going to take the limit as delta x goes to 0, and by doing that, I've created something very common for us. If I take the limit as delta x goes to 0 of dy over dx, isn't that just the derivative, right? Isn't that f prime? F prime of x plus 1 dx, delta x. And of course, I want to add up all of these little segments, right? An infinite number of them across the whole thing. So I'm going to integrate from a to b. And that's going to get me all the little line segments from a to b. So let's recap real quick that bottom part. Delta y over delta x is slope. And if I want to make delta x really, really small, well, now I've actually got my derivative, right? If I take the limit as delta x goes to 0, that's our old-fashioned, f of a minus f of, f of x minus f of a over x minus a technique. Okay, so this becomes the derivative, that's f prime, still squared. This 1 comes along for the ride, that's not affected by delta x. And then my delta x really turns into a dx when you go ahead and integrate. So our actual formula that we're going to use for arc length is this. F prime of x squared plus 1 dx. This will get us the length, the length of any curve. Let's go back to our original problem and try that. Okay, here's the original problem. Arc length is going to be the integral from 0 to 5, the square root, f prime of x. Well, f of x was y equals 2x plus 3, so f prime of x is 2, right? So it's going to be 2 squared plus 1 dx. So that becomes 0 to 5. This is the square root of 5 dx, which is, the antiderivative of square root of 5 is just square root of 5x, right? It's just a constant from 0 to 5. 5 radical 5 minus 0.
Gabriella Giroux, please report to room 318A.
And
Gabriella Giroux to room 318A.
Oh, geez. All the way back here. Why didn't you guys say something? This is obviously 5 radical 5, right? Square root of 25, square root of 5. Not sure where the 3 came from. So if this was 5 radical 5 in the first place, I should have just done it with calculus in the first place because I can't seem to do geometry. So that takes care of that, that takes care of that, and that's your basic arc length formula. Okay? In the next video, I'll do some more bookish kind of problems, as well as an AP style one. Okay? Good luck.
With the following students.